Here we are in 8.3 Piecewise Functions. All right, this is going to be your favorite. All right, so up to this point we have been doing functions, like f of x is a function, where we only have one single equation. In many real-life situations, one single equation won't suffice, okay? And we will have equations that look like this, where we have this is called a piecewise function, where we have one function, but we have multiple equations that are defined only at certain parts of the domain. So for example, the first one is 2x minus 1, but that only applies when x is less than or equal to 1. Okay, and then the other equation, 3x plus 1, that only applies if x is greater than 1. Right? So if we were to take like a little graph of this, let me just zoom in here. Let's see if I can fit this in here. So if we did this kind of graph, just going to put some ticks in there really quick. Okay, so here the first equation, I'll do it in red. Our y-intercept is -1, so right here, and the slope is 2 over 1, so it would rise over run. Okay, and we'd do it the opposite way too, something like this. Okay, and that's not perfect, but hopefully you'll understand what we're doing. But here we're only doing it for x is less than or equal to 1. So it would stop at this point, and that would be one part of our equation. All right, the other equation is 3x plus 1. So the other one, our y-intercept would be 1, and the rise over run would be up 3 over 1. Okay, and you do it over and over again. So this is more steep of an equation, but it only applies when x is greater than 1. All right, and since it's only greater than, not equal to, then it wouldn't include that point. So sometimes we would write it as an open point, whereas this one is a closed point. And we'll talk more about that. I just want to kind of get you an idea of what we're going to be doing. All right, so like I mentioned, some real-life problems, functions are represented by a combination of equations. So I'm just going to go all the way back to the end of your notes here. These are some possible real-life situations. Okay, and I'd like you to come up with an example for A that could be like a real-life situation. I'm going to do B to give you an idea. So first one, you could say something like, looking at this graph, the red graph, it looks like we could say it's a person, a guy named Todd, okay, and Todd is climbing these ladders, okay, up to the very top. It's against a tree or something, and Todd is grabbing this rope swing, okay, and he's going to swing all the way up over here, and he lets go and falls into a pond or a lake, and he surfaces here in the water. Okay, so that could be like a real life situation. You could come up with a different one, and I prefer like you try and come up with something creative. So for A, try and think of, pause now if you can, pause, and write down a situation that could be plausible. Okay, you could have this for your x values. You could have time, you could have distance, etc. And then for like y, you could have height, you could have temperature, okay, or you could do like speed, velocity, things like that. So give that a shot, pause, and come back to me when you've come up with something. All right, hopefully you did that. If not, you can just listen. Okay, so we had lots of people in class that had good ideas. You could have somebody climbing up a ramp and then walks across a flat place and then goes back down a ramp or something like that. And that could be like distance. would be our x value. You could also do something, somebody came up with an awesome idea of like having it being an oven. So you heat up the oven, the temperature increases until it's preheated. You cook something until you're done, and then you turn it off and it slowly cools back down. Okay. Somebody talked about doing like an airplane that takes off, reaches its cruising altitude, and then descends back to the next airport or something like that. Okay, so there's lots of different choices, different ways. Be creative. Something like this could be on the test. And then these ones, in example 4, these are like the opposite. So they give us a problem, a situation, and you'll want to come up and say what kind of graph that would look like. You don't need to write down numbers. Just take like an x value and a y value and come up and say what that could be like. So try and do A and B, pause and give that a shot, and then come back to me when you're ready, okay? All right, so here we have John. He's taking his dog for a walk. So here maybe we could do time, and this could be like distance. Okay, so he's walking. His distance increases as he's walking, as time goes by, but then he needs to stop to tie his shoe. And then, so his distance isn't changing. He's staying at one spot over time. And then once he's got his tie shoed, he can continue walking. Okay, so that could be like a real life situation. All right, B, Mandy is running a 5K at a constant speed. The last 1K, he sprints twice, or she sprints as twice as fast as before. So here you could come up with something like she's running the first 4K. This would be like 4K. You don't need to write down these numbers or anything. But then the last K, for 5K, she sprints twice as fast as before. Something like that. All right? So hopefully that kind of makes sense. This is why we would perhaps need to use piecewise functions, because you wouldn't be able to come up with a good model without doing piecewise functions. All right, so let's go back, talk more about how we use piecewise functions and how to evaluate piecewise functions. All right, so let's look at the first one. We've kind of talked about this before. So f of x, we have these two equations. This equation only applies if x is less than or equal to 2. And the other equation, 4x plus 1, we use it only if x is greater than 2. All right? So let's just label these two equations so that we can refer to them easier. So we'll say this will be equation 1, this will be equation 2. All right, so we want to evaluate this piecewise function when x equals 0. Okay, so what we're going to do is we're going to say, well, when x equals 0, is 0 going to be less than or equal to 2, or is 0 going to be greater than 2? And you'd say for sure 0 is going to be less than or equal to 2. So we will use the first equation. So we'll do f of 0 equals 0 squared minus 1 equals negative 1. Okay. Next one, we have when x equals 2, are we going to use situation 1 or situation 2? Well, we'd look at this and say, is 2 less than or equal to 2? Yes. 2 is less than or equal to 2. It is equal to 2. So we will still use equation 1. So we'll do f of 2 gives us 2 squared minus 1 gives us 3. Okay. Last one, x equals 4. So we'd say and look at this is what we call our domain. Okay, and we've talked about domains before. Usually domains go from negative infinity to infinity or all real numbers. But when we have piecewise functions, they are kind of broken into different pieces. So our domain is broken into, like this one, our domain's broken into two pieces. Okay, so we'd say x equals 4. Is 4 less than or equal to 2? No, it would not. But 4 is greater than 2. So we would choose situation 2. So do f of 4, and then we'd use this equation, 4 times x, where x is 4, plus 1 gives us 17. All right? So if you can, please pause and give a shot on B. Difference about A and B from example 1 is this, they just write it as an f of x. So we want to evaluate where f of negative 4. So it's kind of the same thing. We're just going to evaluate when x equals negative 4. All right? All right, so pause that, give that a shot, and come back when you're done. All right, so here we go. We've got these 1, 2, and 3 different equations. And we're going to see for A, where an x equals negative 4, will that, in which domain, so these are our domains, will it fit? So is negative 4 going to go in here? Is negative 4 greater than or equal to 5 and also less than negative 1? Well, it is. Okay, so we would use 1. So we do f of negative 4 equals negative 4 plus 1 squared, which is negative 3 squared, which is 9. All right, next one, f of 0. Is 0 greater than negative 5? Yes. But is 0 less than negative 1? No, it's not. So we'd go to the next one. Is 0 greater than negative 1? Yes. And is 0 less than or equal to 3? Yes. So we would use situation 2. So f of 0 would be 0 minus 1 equals negative 1. Okay. Next one, we'll look at 3. All right. Let's just erase this a little bit. I'm sure you're going to be able to do this much quicker than the way I'm explaining it to you, just because I want to make sure that you're understanding. So f of 3, this is like when x equals 3. Does 3 fit between negative 5 and negative 1? No. Does 3 fit between negative 1 and 3? Well, you would say maybe, but we'll look at this and it says x is less than or equal to 3. And 3 is equal to 3, so we would choose 2 again. All right? Because 3 is less than or equal to 3. So we'll do f of 3 equals x minus 1, which is 3 minus 1, gives us 2. Okay, last one, f of 18. Okay, and we can go over this one more time. 18 does 18 fit in between negative 5 and negative 1? No. Does 18 fit in between negative 1 and 3? No. Is 18 greater than 3? That is true. So 18 is greater than 3, and we would use situation 3. So f of 18 equals 2 times the absolute value of x, where x is 18. Absolute value of 18 is 18, gives us 36. All right? So hopefully that's all right. Come back and ask questions if you have any. Okay, and then we're just going to do a quick review about graphing like we've done before. You can do it by transformations, or you can calculate the vertex and use the growth pattern. I think we went over this in detail for 8.1. All right, so here, I just need to make sure you guys are understanding that both of these equations, this is like a times x minus h squared plus k. And for this equation, for b, this would be y equals a absolute value of x minus h plus k. Okay, so these values are, they use them exactly the same. So if we wanted to find out what the vertex is here, where vertex is h comma k, would have -1 comma -3. Because when you plug something in, or plug something out of a parentheses, it will switch the sign. Okay, because it's already negative in our equation. Okay, same with b. Our vertex, what would be our vertex? It would be 3 comma 2. All right, and then we'd also want to maybe write down what a is. And pay attention to this because you're going to need to be able to do this on our next page. So a here would be 1. It'd be right here in front. If you didn't have it, it would just be 1. And for b, a is a -1/2. All right, so now we should be able to graph both of these. So first we'll do a vertex, -1, -3. We already have it there pointed. And then a, since it is a quadratic, we have something squared, we will do our growth pattern. 1a, 3a, 5a, and if you needed to keep going, it would just be all odd numbers. Okay, so here a is 1, so we'd get 1, 3, 5. We'll go over 1, up 1, over 1, up 3, over 1, up 5. Okay, and you could keep going if the graph had more room. And then we would just graph our parabola. Okay, something like that. Okay, if we did it with piecewise, or not piecewise, absolute value function, okay, we'd use the vertex again, so which would be 3 comma 2. And then instead of using it as a growth pattern for a, we're using it as a slope. So we will do it on the right side of our vertex. So we'll go down 1 over 2, down 1 over 2. Okay, that gives us half of our absolute value function. On the other side, just like we did with the vertex, or with the vertex form of our quadratic, we reflect it over the axis of symmetry. So we will just mirror it over, okay, like that. And that would be our graph. Okay, so it's very similar. The two equations are very similar, except here with the quadratic, we use our growth pattern for a, 1a, 3a, 5a, and with b, where we have a absolute value function, we use a as our slope for our right side, and then just mirror over to the left. Okay, c is also a quadratic. We'll go on and do the other stuff. Okay, piecewise function, or graphing a piecewise function can be done in one of two ways. Okay, so one way is to graph all of the equations. So for example, for 3, you could graph this whole equation, and we'll do it right now, x plus 1, so this will be our y-intercept. So this is like y equals mx plus b, where b is your y-intercept, and your slope here would be positive. So we just do our best to make it a straight line. Okay, and then our other equation would be -x minus 2, so we'd have our -2 would be our y-intercept, and our slope would be -1 over 1. Okay, and that would continue all the way to -infinity. Okay, all right, the next step is, it says write all the equations and erase any pieces that lie outside of the given domain. Okay, so this is our domain. This is like our domain for the first equation. This is the domain for this second equation. All right, so all x values. right? So what we need to do is erase the ones that don't pertain. So the red graph is only for x values less than 2. So we will erase everything all the way through where x equals 2. And then for blue, it's all x values greater than or equal to 2. So we will erase all of these all the way to 2. Okay? And then at that point, there's one more step that we need to do, and these should go to infinity, okay, is the end of the points. And I think I've had some of the students talk about how you've learned how to do this before, at least with inequalities. So here it goes with this. So here we have an open, I'm going to call this a point, open point, something like this. When you're using inequalities like less than or equal, or sorry, less than or greater than, okay? So these are your two, less than or equal, less than or greater than, okay? You would use an open point. So for example, our red equation, x plus 1 is when x is less than 2. It doesn't include 2. So what we'd do is we'd leave an open spot at that point. Okay, and then the other equation, we have x is greater than or equal to 2. So these are the ones where they will include the point. So less than or equal to or greater than and equal to would be filled in points or closed points. Okay, so for that one, since it's x is greater than or equal to 2, we would fill that in. All right, so it's completed. That we'd get 100 points or 100% on that problem because we drew both of the functions and we had the right domains and our endpoints are marked correctly. Okay, so let's look at B. So there's another way that I said. One way is to draw lines where the graph changes. So in effect, these are the points where they change, where they start, where they end. Okay, so it says draw lines where the graph changes and only draw the graphs within those boundaries. So for example, we can start with here. We can say a vertical line where x equals -3 would be here, make a dotted line. Okay, and it goes all the way to +5, which is right here. Okay, so here we would want to only use this equation between these two, like the edges of those domains. Okay, so x minus 2, this is our y-intercept would be -2, and our slope is 1/1. So this would be like 1/1x minus 2, which is our mx plus b. So our slope here would go up 1/1 all the way until you hit that boundary, and you'd stop. Then we would look at the inequalities. So this one, x is greater than or equal to -3. So we would have a closed point because we include that. The other side, x is less than 5, but does not include that point, so we'd have it be open. All right? The other equation, it goes from 5, we already have a vertical line through there, and we also have it's less than 9, so here we put another vertical line for our other equation. Okay, and this equation is y equals 6. Okay, so if you look at that, you can kind of say, well, if we did y equals mx plus b, the slope here obviously is 0, because we don't even have an x in there, so we just have y equals b, where b is our y-intercept. And the intercept is at 6. So it doesn't matter what x value, it's always going to be 6. So we would come here, make sure that's, okay, it was a little too high, right here. Okay, so this would be the equation y equals 6. That is only between 5 and 9. Okay, and we need to find the endpoints. So if we look at 5, we would see that x is greater than or equal to, it includes that, 5 point, so it would be filled in. The other side would be x is less than 9, so it doesn't include that point, right? So hopefully that makes sense. I know these ones are like the easier ones, and we have some below. I'll probably go and do those as well. But please, if you can, pause so you can give it a shot by yourself. Whenever you can, pause if you feel like you're understanding, or even if you're not understanding, give it a shot so you can see where you're making mistakes, okay? Don't just write down these notes and as I do it, because that won't help you as much, okay? All right, so next one. Our domain for our first equation goes from -9 to 2. So I'll make my vertical line for -6 and +2. Okay. And then, excuse that, here we would look at this equation. So this is an absolute value function, and we talked about this before. Okay, let me go back to it. So it is this type of equation where we have an x and a k, and will give us our vertex, and a will give us our slope. Okay, so we'll go back here, right here, okay. So we'd say, what is our vertex for that equation? So this would be like our h, and our k would be like +0. So our vertex would be -4, 0. Which will be right here. And then this is our a value, which is 1/2. Like I said, that will be your slope because we're doing an absolute value function. So we'd go up 1 over 2, up 1 over 2, up 1 over 2. And then you'll reflect over this axis of symmetry. So it'd be something like this. Okay? And we look at the endpoints, the left side, since it says x is greater than or equal to -6, we would include that point. And then on the right side of our equation, it says x is less than x is less than 2. So it does not include that point. All right, so we've got that half done. The other equation, it goes from 2 to 8. So we'll go from 2, we already have that line, and then we'll just go to 8, which is right here. Okay, and we're going to graph. Here we have like mx plus b. This is a linear equation where -8 is our y-intercept, and our slope is up 2 over 1, up 2 over 1. And we will just continue that pattern all the way till we hit that boundary. Okay, so I realize that we started, that is outside of our domain, but that helps us so that we can start graphing. Okay, but we will only connect those dots that are inside that domain of 2 to 8. X equals 2 to 8. Okay, sorry, I just really I just redo that. Okay. Something like that. Okay, and then we just have to look at the ends. Okay, the left side says x is greater than or equal to 2. So here we'd include that point. Other side, x is less than 8. That does not include that point. We make it an open spot. So whenever you have inequality that has like that flat on the bottom, that's the like equal to, those are the ones you will fill in. The ones that do not, you will have them open. All right, last one. Okay, we'll do our vertical line. It starts from -infinity to 3, so we'll just make this vertical line test, or not vertical line test. Sorry, it was a late day, or yesterday. It was parent-teacher conference. I had an interview. It was kind of crazy, and I was also observed by the assistant principal, so it was a busy day. All right, so we're basically saying we're using this equation wherever x is less than 3. So we're going to be using this part of our graph. Okay, we want to find our vertex. Okay, we pull that out, that switches its sign, and then we have -8. So our vertex is right here. And then we will use our growth pattern because this is a quadratic. We have a square, an exponent that is 2. So it's going to be a parabola. So since a equals 1, and we want to use 1a, 3a, 5a, we'll go over 1, up 1, over 1, up 3, over 1, up 5, over 1, up 7. And you'll just mirror over to the opposite side. Okay, connect the dots. Okay, and to the other side. And it stops once you get to the edge of that domain. Okay, we need to find out, is that going to be an open point, or a closed point? Okay, and I kind of covered that up. Since it says that it's x less than 3, it doesn't include 3, then we'll have it be an open. All right, our other equation, this is also an absolute value function that we did over here. We'd need to find the vertex. So the vertex here would be h, which would be inside the absolute value function. Since there's nothing there, we would say it would be 0. And then we'd have -4. So that would be our vertex, would be like right here. Okay? And then our slope is our a, which is just 1. We'll go up 1, over 1, up 1, over 1. And that will continue to infinity, but we'll only draw the line that's in the right domain, which goes from x is greater than or equal to 3. And since it's greater than or equal to, we have a closed point because it includes that spot. And if you wanted to, you could erase the points that you drew to help you do your graph. Okay, and that's it. So hopefully that is a help for those who needed extra help or were absent. We have one last thing we need to be able to do. So in example 1, they gave us the piecewise graph or piecewise function. Okay, we'll also need to be able to do it oppositely. So we'll give us a graph. We need to write down our piecewise function. All right, so I like to do this first by writing down the equations. So like, for example, the red for A, the equation would be, we'd say, well, this is linear. It's in a linear equation, something like y equals mx plus b, where b is our y-intercept. So b here would be 3, and our slope, which is m, would be rise over run, is just 1. So our equation would be y equals 1 times x, or just x, plus 3. Our other equation here, this is a quadratic. It makes a parabola. We'd want to find out what is our vertex. Well, our vertex is right here at 1, 0. And what is our a value, our growth pattern? We'll go over 1, up 1. Okay, so since it goes up 1, after you've gone over 1, that gets to know that a is 1. So we'd write down our equation. Remember, have this memorized. For vertex form, it would be a times x minus h squared plus k. So we'd get y equals a, which is 1. Okay, and you don't need to write that down, but you'd get x minus 1 squared. All right, and if you remember when we talked about shifting and things like that, that means that it was shifted right 1, which makes sense because it's not at 0, 0. It's been moved over to 1, 0. Okay, so those are our two equations. Now we're just going to write it as a piecewise function. Okay, you look at those other examples that we did. It was always something like f of x equals, we'd do that little bracket, and we'd write our two equations. Okay, so here we'll do f of x equals, we'll make this little bracket. We'll write down our equation. So we get x plus 3 would be one of our equations. The other is x minus 1 squared. Okay, we'll put a little comma to put in our domain. So our domain is all x values for our red graph will be our first one, okay? So this arrow continues going all the way to infinity. So you could write it as negative infinity is less than x, which is less than 1. And since that is an open point here, it wouldn't be less than or equal to 1. All right? Oftentimes, you would not write that, and you would just say all x values less than 1. That's how you will see it on the test, and probably on your homeworks and your quizzes. So, but either way, if you did it on the test, I would not mark points off, okay? Okay, the other one, the domain from here to infinity, okay, that would give us, it would start at 1, and it would be less than or equal to x, because it's a filled point, and you could write it as less than infinity, but again, it's already covered. So that's the other thing, is oftentimes when we have an end point that goes to positive infinity, we would switch this around and we would just say x is greater than or equal to 1. Okay? It's just what we usually, that's just standard how we write it. But do it that way if you can, and you probably wouldn't miss too much if you had it the other way around. Okay, it's just how it's usually taught or shown that way. Okay. Anyways. Okay. All right. One sec. Okay. Now let's do example 2b. So we have 3 separate equations, and we will want to write those down individually. So our first one, we'll do y equals, and you gotta remember that this is a linear equation, it's straight, okay? And if you want to, you can continue that on and find out what the y-intercept is. So here the y-intercept would be 0, okay, and the slope would also be 0. So for y equals mx plus b, you would end up just getting y equals 0 would be our equation for that graph. Okay, for the next one, this is a parabola, so it would be like y equals a x minus h squared plus k, where h and k is our vertex, so our vertex here would be 0, 4, and our a value would go over 1, and it goes down 1, so a would be negative 1. So we plug those in, would end up getting our equation y equals negative x minus 0 squared plus 4, or that's the same thing as negative x squared plus 4. Okay, so that would give us our equation for that. And then for the green, we can continue that line going to find out what the y-intercept is, which is 3. So if that's also a linear equation, y equals mx plus b, y equals m, which is our slope. We go over 1, down 1, or I guess down 1, over 1 would be our rise over run. So it'd be negative x plus 3 would be our other equation. So now we'll just write it as a piecewise function. So f of x equals, and it will go from the first equation is 0. The next equation is negative x squared plus 4. And the final one is negative x plus 3. And now we just want to find out what the domain is. So the red one, it starts at negative 5, okay, and ends at 2, or negative 2. Okay, and these will always be less than or less than and equal to. So you can always start like that, and then decide, does it include that point? So here, at negative 3, it includes that point, right? The only case where you would need to have it as the opposite direction, so greater than, would be if you were like at the end of a like we did for the last problem, where we did x is greater than or equal to 1. Okay? All right, so since all of these will be the same. So next one will go from, blue would go from -2, which is less than x, which is less than 1. And that includes that point at 1, so we do less than or equal to. And then the last one, it starts at +2 and ends at 5, and it includes that at 5. All right, there's one thing that we need to notice is that here in between red and blue where they connect, it doesn't show that it's a filled point, doesn't show that it's empty. So you would just need to choose which one you wanted to include that point. So you could have it be there to include that -2, or you can have it on the other side like this, okay, as long as that point is filled. If neither of them were filled, then you would have an open point and you would find a blank spot, okay? So you just need to choose which one you want. Make sure that it's not missing that point, okay? And this last one, this is kind of like the same thing. It doesn't show us which side is using which, and it'd be just very similar to that. So I'm just going to leave that one for you if you'd like to use it. And that covers everything. I'm just going to look at the homework really quick in case. What do we got here? So here we've just got some examples, like the first ones we did, where you will evaluate where they belong. So for example, -3. We would look at -3 and would say, is -3 less than 2? Yes, so we would use that equation. Okay. Or for example, if x was, for this one, let's say this one would be 5. We'd want to see where that's going to go. Is 5, for this one, is 5 less than -4? No. Is 5 greater than -4? Yes. Is it less than 5? No. We'd use this one because 5 is greater than or equal to 5. Okay? And here you'd be graphing. Piecewise, make sure you're only graphing for the domain. And then more of that. Here you'd need to write down the equation and the domain. So when they're talking about writing the equation and the domain, that's just saying the f of x, writing the two equations, and then doing the comma and the domain. Just like that. So this would be like the domain for this equation. This would be the domain. All right? And this one, use that as well, the domain for those. Okay, and then here we're just going to sketch the graph based on this wording, just like we did in our notes. And then here we would write down a situation. Okay?